These are the problems that are on the worksheet for class today. There are a series of problems about graphing quadratic functions. So you've got a sense that the shape is always going to be in terms of quadratic. So maybe I could draw in what I expect the shape to look like, something like a base curve, something like that for y equals x squared. And this is a particular quadratic, a parabola with vertex at 0, 0. And you can kind of get a sense of the scale by realizing that with y equals x squared, when x is 1, x squared is also 1. So then there's a symmetrical point, x is minus 1, x squared is 1. So that's kind of a way to anchor the quadratics with the vertex location and to have a sense of the scale by a point that it goes through. And then you can see what the variations are and what effect that has on the quadratic. So for instance, y equals 3x squared. Still, when x is 0, y is 0, so it goes through the origin. But all that's different is that factor of 3 out front means that the function values, the y values, are scaled by times 3 from what they would be on that default parabola. So in particular, when x is 1, the value is 3. So here's 1 over and 3 up. And when x is minus 1, the value is 3. And you get a parabola that is a steeper shape, something like that, for y equals 3x squared. Y equals minus 1/2 x squared. Well, again, the vertex is at 0, 0. They didn't indicate that point on the scale, but you can see that 0 on the x-axis is between minus 1 and 1, and 0 on the y-axis is between minus 0.5 and 0.5. So that should be the origin. And this time it opens down. When x is equal to 1, its value is minus 1/2. So 1 minus 1/2. So it's a shallower parabola, something that opens that way. But the characteristics that you might note is that it opens down because of this negative exponent, and it has a vertex at the origin. So there's that one. Those couple. Let me take a picture of this. And clear the ink and look at the next couple. This time I have a little bit more interesting transformation. This is going to be one where the pieces are going to be kept track of with two transformations, and to figure out what they are, I have to go through the process of completing the square. So I'm going to write it as y equals minus, and x squared is there. I'm going to bring the linear term in, so instead of plus 2x, the minus out front makes minus 2x. Leave space for whatever constant I need to complete the square, and the constant that is in that one is plus 1 still. So factoring the minus out makes this equation at the bottom the same as y equals minus x squared plus 2x plus 1. But now inside the parentheses, x squared minus 2x, I could make that a perfect square trinomial with plus 1. The overall effect is minus 1 when I put that 1 in parentheses, so I'll balance that minus 1 with a plus 1. And that makes the equation equivalent to the one I started with in a slightly different form, minus x minus 1 squared, that's x squared minus 2x plus 1, plus 2. So that's, when I write the equation in that form, I've got all the information I need to graph it. I need to do a horizontal shift, 1 unit to the right. That's the x minus 1. 2 units up, and the negative here means that the parabola aims down. So that bit of algebra changed the equation into a one where I can read all the geometric information I need to know what the graph looks like. So I'll start at the origin and go 1 unit right, 2 units up, and this is where the vertex is going to be. And now I want to make a parabola aiming down from there. So a shape like that is the shape for that curve. Same trick for number 4. This time I will write y equals, factor the 2 out, and it's x squared minus 8x. That's the minus 16. Now, I could have factored an x out, but that won't help me with my completing the square strategy. So the plus 33 is still there. Now what I need inside the parentheses to make a perfect square trinomial is x squared minus 8x plus 16. 2 times 16 is a plus 32 that's been added to the equation, so I'll subtract 32. So this is the same thing as 2 times x minus 4 squared is that trinomial, plus 33 minus 2 is plus 1. So now I've got what I know what I need. X minus 4 means 4 units right. Plus 1 means it's 1 unit up. And times 2 means that I stretch the parabola on the y-axis. So let's do those things. Start at the origin, which they would be there on the graph they give. 4 units over, 1, 2, 3, 4 units over, 1 unit up, and scale it by 2, so a little steeper, and I get a parabola that looks like that for that particular quadratic equation. Save this one. Clear my ink and go up to the next couple. X squared minus 8x plus 13. You know, I noticed that this worksheet has the graphs to do, and it's not automatically centered, so they kind of give you a clue that if the parabola you want to draw doesn't fit on the scale that they give you, maybe something's gone wrong. So let's see. I will write that as y equals x squared minus 8x. Complete the square is plus 16. So plus 16 there, minus 16 keeps the equation the same. So it's x minus 4 squared minus 3. X minus 4 squared means I go 4 units over from the origin. So there's the origin 1, 2, 3, 4 units over. 3 units minus, so down 1, 2, 3. Here's where the vertex is. And the equation then would be up from there, so a shape like that. There's lots of stuff that I could find in addition to this. It might be interesting to know where the thing crosses the y-axis. It crosses it when x is 0, so that would be at 13 up above where I've drawn it, figuring out the y-intercept that way, and then I could also have x-intercepts there and there, solving the equation x squared minus 8x plus 13 equals 0. Useful stuff to know, but that all follows from the graph if you've got the graph. So what happens for the only change being to make a minus x squared? That's the only change for number 6 from number 5. But what I'm going to do is write it as minus x squared, now plus 8x, to make, in parentheses, a term that matches the minus 8x originally. It was minus 13 is the original constant. X squared plus 8x, completing the square, is plus 16. So overall, it was minus 16 to get the change with 16 inside parentheses with the minus out front. So minus 16 is balanced with plus 16 to keep the terms in the equation equivalent. So it's minus, for this one, x plus 4 squared plus 3. X plus 4, so I go backwards from the origin 4 units, to the left 4 units, and up 3 units. It wasn't that nice of them to give me that as a scale so that this will fit. And now it is negative out front, since the point of that is that it makes the parabola open down, and I get a shape like this for that curve. It's quite different looking from the original one. Just changing one sign in the equation made a big difference. So I'll capture that and clear my ink so it won't show when I scroll forward. And here are the last couple problems. These are given with the work done already so that I don't have to worry so much about completing the square. X minus 3 squared, so over 3 units from the origin, 1, 2, 3 units horizontally, plus 1, so 1 unit up. Here's the vertex, and it opens upwards. Maybe something significant to notice about this parabola is that it has a symmetry. We talked before about symmetry of functions, even symmetry or odd symmetry. For a typical parabola, the place where the symmetry would be, the mirror image line, is a vertical line through the vertex. So the equation for that line would be x equals 3. 3 units over, and that vertical line, x equals 3, because there's no y in it, x equals 3, you might think of as saying x equals 3 no matter what y is. X is 3 when y is 1, or y is 0, or y is 2. It doesn't matter. All possible values of y generate the terms on that vertical line. So that's the axis of symmetry. That's a value that's kind of nice to know. Another one, the last one, 1/2 x minus 4 squared minus 2. I see 3 things that are done. X minus 4 means from the vertex at the origin, which would be for y equals x squared. X minus 4 moves me 4 units to the right. Minus 2 moves me 2 units down. This 1/2 out front of x minus 4 makes it a parabola that opens shallow, so a shape that looks like that. But still, that basic arch with that same symmetry that all of these quadratic functions have for their graphs. So that's the variations on this problem of figuring out what the graph of quadratic function looks like.